Okay, so we're now going to look at our second version of the coding breakdown on the C++ program, along with the algorithms, and that's going to be in a PDF. And then we're also going to show you an HTML equivalent. It's supposed to be like a PowerPoint slide deck, which is HTML. That's also provided as well. You can find that here in the slide deck right here. Just open up a browser. The other one that we're looking at right now is the coding breakdown right here, this one. So let's do the code breakdown with the PDF first. So here you should be able to see the source code while we go through this. So it's the same C++ as the prior video, um, as shown pretty well here. This one found in the appropriate subdirectory path. Again, in Windows subsystem for Linux. In this case, Ubuntu 22. All right. So what we're looking at is an overall executive summary. We're using C++ 20. We've shown how to build it in the prior video. We're using this model here for optimal market making, which is kind of popular. Alavanida Stoikov with an order flow imbalance, signaling to improve the quoting placement. Again, this is trying to do sub microsecond task processing in C++ 20. And I have to stress this very importantly. When I'm developing these, I'm only using standard template library. There's no external libraries. So I'm forcing the AI to generate all the algos for me. That's important because I'm not using any form of external third-party libraries at all. That will help reduce the size of the file, the executable, and also minimize extra extraneous processing. As I said, this is using Ubuntu, Linux. The throughput, it says, can go as high as 3 million. Here it's saying it's 1 million ticks per second. The overall architecture, market data handling, the strategy engine, the order manager. So one-to-one here with an order book manager, volatility estimator, OFI calculator. And then there's a low latency infrastructure code as well with SPSC queuing, which is lock free. And I've said this before. This is probably the most popular post or topic I have on my website on the relaunch quantlabsnet.com. So our timestamp we're using is RDT-SC. We're also using fast math utilities because the AI is generating it. All right, so here's again, the layered architecture. And it's all layered, all in one self-contained file, as I've shown before, something like 1,700 lines. And here's all the code here. You can go through the code here on your own time, investigate it all. You can modify it, whatever. This is just, again, a sampling of one of thousands of techniques based upon performance, market condition, um, assets or instruments that you want to focus on that may be trending or however you want to, whatever trade with high volume, high liquidity, and also specifically what strategy you want to use and set of algorithms as well. It's a number of factors here. As I said, I'm choosing purposely Bitcoin. It's the most popular. Although this is not the most optimal for this data set on the Bitcoin data, on tick data for 2 days worth that I've shown in the prior videos, market making is easily the most popular. So that's what I'm choosing and that's why I'm using it. All right, so again, we have 1,700 lines of coding, all again generated by AI. So here we have 4 different layers. Going from the top, we have the application layer with a CLI, backtester, parameter optimizer, live trading engine. And then you still have to hook up all the market data, like real world market data. It's all simulated as is right now. And also the rhythmic trading market data connection along with the rhythmic order execution using the rhythmic C++ API. So that's not here. I would not be giving away this or even selling it, whatever, at least whatever. Can't do it. Terms of service don't allow me with the rhythmic API. So I cannot show any code, any information regarding rhythmic. There are workarounds for that. Email me and I'll let you know what they are. It's not a cheap option. This is institutional level stuff. So here we have our strategy level, the strategy itself for the core strategy, the quote generation, the fill detection. Layer three, the next layer we have market data, order book, volatility estimator, order flow and balance, and the market data simulator. Here we have infrastructure layer, SPSCQ, timestamp, a fixed point for the arithmetic, the fast math utilities, and the circular buffer. So that part of that loop ring. And then here on the layer, the bottom layer, we have the compile time constraint, compiler hints, and cache alignment directives. Okay, so again, the data flows like this. So once we have real live market data, and I'll tell you this, if you're trying to plan to do this with interactive brokers, it's pointless because it's not true high frequency trading. It's easier, but it's not true high frequency trading. You're not getting tick data. The best you can get is uh, 1 minute data through interactive brokers. With a fix, it may be different, but I still would have you use Rhythmic because it's cheaper. The cheapest option out there, as is what I'm showing you and what I've talked about in various videos. So we have the tick data, 32 aligned structure. You'll see that in the HTML on how it's done and why it's done. Again, AI, and it's done optimally on purpose for high frequency trading purposes. Then it communicates with order book with a mid price updater. We have a volatility estimator with the OFI calculator. It binds everything into a reservation price, the optimal spread, the quote, and then we're going to deal with the exchange or the simulator. Here in the quote, we have the bid ask price and the quantity. So here's the building system. We've kind of gone through this already. The different switches, how to do it optimally, the build flags and all that. So I don't need to focus on that at all. So here's the first section, which is the include headers and dependencies. These are all, as I said earlier, standard template library, and I've also explained why. Here we have our compile time configuration. So these are all our parameters that we set for the compiler. Here, cache limit size. So if you're not familiar with C or C++ on the caching, this is where you learn. We have so we're assuming you're going to use a modern 8664 CPU. There's a 64 cache byte, 64 byte cache line with a data structure for cache line boundaries that prevents false sharing in multi-threaded code. Okay, so this is optimally done for you with the AI. Again, I'm just showing you the demonstration of it. So we have a 64 byte cache line, the thread of 8 bytes, padding of 56 bytes, and then the 64-bit byte cache line again with a thread 2 data, 8 bytes, padding at 56 bytes. So we're using always this power of 2 buffer size. So it must be used for the ring buffer sizing, and that's for the efficient modulo operation. So here we could have slow actual division using the index, and so on. And here we have our risk limits that we set, max inventory, these are the maximum open position sizing, max position value. So well, in this case, we allocate only 1 million of notional value and exposure, and the max drawdown percentage. So you could, in theory, once it starts losing 5%, you can automatically shut it down. And that's the sort of thing you want to use as part of your kill switch as well. If it does go out of control, and you do go through to regulate this for, let's say, going on direct market access, you will need to explain how your kill switch works. This is it right here on the max drawdown percentage and the logic that you use to have your bot, program, whatever, shut down automatically. That's the automated kill switch. Again, here we have our different hints and attributes for the compiler. If we're forcing inline, hot path, cold path, the likely, unlikely as well. So the built-in expectation. Here we have the attribute explanation using the GCC attribute and the effect of it and the macro that you'll use. Here's a branch prediction as well. without hints, with hints, compiler optimizing the common case using this unlikely flag. So we have a generated assembly difference in the branch layout. Likely paths fall through for expected cases, unlikely path for unexpected cases. So we also have the cache align template. Here's the format for that. Using templates, which kind of minimize part of the processing. The template ensures wrap type occupying exactly one or more complete cache line. So for a 4-byte integer, the padding will be 60 bytes as well as total. This is kind of helpful too, having a high resolution timestamp. There's a code snippet right here. Um, Again, wall clock nanoseconds. And as I said before, when you go direct market access, everything's measured in nanoseconds, nothing but. We have a timestamp counter value, forcing inline with static template. That's pretty good. And then we have the RD real time stamp counter, which is this RDTSC instruction reading the CPU cycle counter. I'm not sure if Rust can go down this level on the instructor. I don't know because I don't know Rust, but I know C++ and C can do that. We have inline assembly breakdown. Why use it? As you can see here, the caveats. Again, this is the important one, the format of this on the lock-free SPSCQ. It's using a template again, and there's your format. Then we have our memory layout with the addressing on the false sharing prevention. Again, this is for optimal C++ techniques. Okay, remember C is one step higher than assembler, and that's obviously going to be the fastest. C++ kind of works with C plus the C++ features as well. So again, push operation, we have our inline um, and memory ordering explained right here. So here we could have relaxed, no synchronization. Acquiring prevents reordering of reads after this, or the release preventing the reordering of the write before this. Okay, and there's a use case of when you use it with the push flow diagram right here. Producer, read, head, relaxed, calculate next position, check if full by reading the tail, the acquire where the write item is buffered, and then the update head release makes the item visible to the consumer. So here we have a pop operation as well, using the template um, techniques, constant tail of the size, and all that fun stuff. And then the pop flow diagram, fixed point arithmetic as well. So again, this is all in the code. Okay. So here we're asking why fixed point for HFT, precision, floating point, speed for the modern FPU, which are quite fast, determination or determinism, which is platform dependent and rounds. It's fully deterministic, meaning it's kind of has predictability. There's a comparison of the epsilon and the exact companion. Here's the different examples of that. We also have market data instructions on the enumerables, which can be pretty standard as well. Order status, order type on the side that you're on, or the buyer, bid or ask, buy and sell, long, short, sort of thing. Design choices, we're using an enum class for type safety, unit 8T type, underlying type for minimal memory footprint, and explicit values for binary protocol compatibility. And again, here's the tick data structure, memory layout as well. And it's a 32-byte alignment. And then this is fits exactly in half a cache line. So we're able to put 2 ticks per cache line, which is highly efficient and sequential access. It's also SIMD friendly and alignment for potential vectorization. Here's the price level structure along with some sampling on the best ask, best bid, best ask. Order structure right here. Standard stuff on the order ID, timestamp, price, quantity, filled quantity on the side that you're on, the type, status, and some reserved for excess padding. So here we have a 64-bit alignment ensures one order per cache line, no fault sharing, multiple thread access, different orders. So again, the coding takes care of all the threading for you. Again, go through the code to learn all that where it's applicable. We have a quote structure. And again, here's a sample of that as well, with a timestamp. So we have something here called circular buffer implementation. We have another template, which is the most efficient with a circular buffer class set, where it's private, meaning the size, the head, the counter, and the standard array as well. So some visual representation there. We have a push, which is inline from what I'm seeing here. We also have an index as well. We have index calculation example on the buffer state, the logical, the oldest element, and the logic. Again, I'll show you this in the HTML version of this as well, which should help you visually see it in line with the code and the algorithms as well. So as I said here, we are forcing the AI to create the algo for us, no third party. It becomes a fast math utility. We have fast algorithm, shroud, golf, fast exponential. How it works. So the trick exploits log2 equaling the bits and all that. So we multiply by scaling constant to handle log t exponential and add bias constants for the exponent offset and reinterpret the bit as double. And here's again the accuracy of it, relative speed versus max error. We are also using this fast inverse square root. This is a Quake 3 algorithm adapted for double. Bit manipulation approximate of 1 square root to the x using IEE 754 exponent with a Newton-Raphson refined with 1 iteration clamp function. We have, this is a really good one, volatility estimator. Here we're using the rolling volatility. Again, you'll see that in the HTML. Using this exponentially weighted moving average. We have class members right here. The variance, the price, the alpha, the min variance, the initialization, update count, and the backup for the rolling window of the realized volatility. So here we have some returns, some square returns, along with the circular buffer on the volatility window. Then we have the alpha calculation. It's explicit for the volatility estimator using these parameters along with the logic. Half-life concept, set of ticks, updates an observation weight decaying to 50%. And here's the formula. And here's some examples of half-life, alpha versus the response. We have also the update logic here as well. And the EWMA update formula right here. And again, we have all the different parameters, variables that we're using within this algorithm. We have volatility retrieval, where we get the volatility using this fast math. Again, that's all internal and runs a standard deviation on the root of the variance. So here we have the order flow imbalance calculator. This can track the balance between the buy and sell pressure to predict short-term price direction. So we have a mathematical definition here of the OFI. So this is in a range of +1, all buying pressure, -1, all selling pressure, and 0, where it's balanced. Here's the implementation of it. Using, once again, order flow and balance with the circular buffer, cumulative buy volume, cumulative sell volume, EWMA, OFI, alpha, OFI, EMA standard deviation, the alpha standard deviation as well. We also have the update logic right here, all that. I'm not going to go through that. It's quite lengthy, it seems. This is the important part right here to understand the window and how it works. So we have a window size of 5 bytes, or no, this is 5 elements. So we have here cumulative B6 to of the S, and then we have a new tick arrives, cumulative B equals 4, S equals 7. So we remove the old B2 and add the new B4. Okay. So we have a normalized OFI. It's like a Z score value that compares across different volatility regimes. You can see the power of this. Limit order book. So we have an order book with the current state of the order book for the bid and ask. Data structure right here. Bid count, ask count, last mid price, last update, and the T sequence with the book structure visualization, which we're not, I mean, you can use in the Python that was showcased here. Here we can see the least aggressive ask, the best type ask, which is top of book. And then again, we have the bid ask top of book on the least aggressive bid. So we have the upside update on the side algorithm. We're using this hot path update as well. I'm not going to go into this. We have an insertion object example as well for the bid size, micro price calculation, micro price intuition, and we have the AS model, which is the actual market making algo core implementation from the 2008 paper that's shown in the prior video. At the end of that video, we have the market configuration gamma. Here's the actual K order book liquidity parameter and the based arrival rate. OFI enhancement with the beta and the use of the OFI as a flag. And then we have built-in risk management on the inventory of the max inventory, max position size, and the inventory target. We have quote parameters, min, spread, max spread, quote size, tick size, and the timing as well. Then we get into the parameter interpretation. We got the gamma. We have, and this is the key here, is the range of each and what they interpret and the symbol as well. So here with the gamma, the higher shows more aggressive inventory management. Higher on here, which I believe, which one's K? Order book liquidity right here. Okay, and A, the base order arrival rate, and then the OFI beta, the weight of the OFI signal in reservation price. Then we have the state management. This is on the actual AS model with order book, volatility, OFI, cash, P&L, realized P&L, unrealized P&L, which is the market to market P&L, peak equity for drawdown calculation, max drawdown, current quotes with the quote and last quote and S as well. So we have a main ticket handler, main tick handler. So it's an on tick using this hot path data structure where we have a tick side and we update the order book as well based upon quantity and price. And we have the order book as well, tick and price and quantity. And then we update the volatility with the order book. And if it's mid, do this, update the OFI, check for fills, generate new quotes if needed, and update the P&L and update the statistics. So we have here the pipeline, okay? Quote generation right there, okay? Reservation price. We have an inventory penalty as well, reservation price itself with the formula right here. The AS reservation price, which where the market maker is indifferent between buying and selling, deviates from the mid price based upon inventory. Then we have the effect on quotes. So here is where it gets interesting. We have a reservation price, which is below the middle. We have both bid and ask shift down or more aggressive selling when you have less aggressive buying. So we have an OFI adjustment. And then we have this formula and we do all this stuff where if OFI is greater than 0, reservation shift up, anticipation price increase, and more aggressive buying. So again, we're not building around charts, all the lines and metrics that come along with the charts in the technical analysis world. Same with the fundamental. This is Bitcoin where it can be unpredictable. We also have the Microsoft blend of the double Microsoft micro price and the reservation price. So this is blending with micro price, providing additional adverse selection protection. And we have the optimal spread, half spread as well. That's all based upon the AS model. We have the profit from the spread with full probability. And again, this is really important to know. When you have a wider spread, we anticipate more profit per trade, full probability, wider spread, fewer fills as well. So we can calculate the optimal spread. And then there's infinite horizon to infinity uh, using stationary form here, getting a quote construction, uh, bid price, ask price, inventory skew amount, and then visually this is what it looks like for the mid price, where we have the skew on both sides and the reservation price in the middle. And then there's a risk control where we enforce it. We enforce spread limit using the spread, min absolute spread, and then max absolute. So if the spread is less than the min absolute spread, do all of these fun things. And then we have inventory limits as well, and then we can aggressively unwind when you're near the limit. And we have the final quote where it's round the tick size, and then we do a sanity check and get the current quote and the quote if the quote's valid or not. So here we have the full detection. Again, the hot path using these check fills. If the aggressive buys little, lifts, or ask, we sell. If the tick side is equal to the bid and the tick price is greater than or equal to the current price of the ask price. Okay, so we have fill logic here, quote, and the bid. And here's the logic here again. Smartly, this is the first time, again, using this trading logic. Could do a market trade, sell when it hits aggressiveness. We have a trade price, and then if it's less than the bid does get lifted, and then you do a buy. On the opposite, with a market trade where there's a buy aggressiveness, the trade price is greater than our ask. The ask gets hit, and then we sell. So we have the P&L calculation. Again, unrealized P&L, equity against the peak equity drawdown as well. Then we have our P&L components of cash unrealized, where the inventory is times the current price, and then the total price as well. And then we measure the drawdown, peak equity minus the current equity divided by uh, peak equity. So we're close to getting done here because it's quite a bit. Here we have a code snippet of generic, synthetic market data using the geometric motion. As I said, you will need to add in whatever your broker or exchange is, you have to use their API. In my case, I can't share the Rhythmic one, but it's built in with this as well. So again, here we have all this data here as part of the tick data. And then we have the GBM simulation using DS here, this calculation for discrete approximation. And then we have the price path example as well with an initial volatility in the various ticks that come with it. Then we have that CSV loader we've talked about here. And if we exceed it, who knows? We have a back testing as well. There's a class simulation loop. We have a result loop as well. The parameter optimizer, where we calculate the optimizer result structure. We have grid search implementation as well. Optimization output, again, showing you the parameter sets here, the gamma, K, OFI, sharp, PNL, max drawdown. We have a so-called live trading engine, but again, we don't have anything connected up to the broker, the exchange that we're using, in my case, using, once again, Rhythmic. We have the thread affinity as well. We'll go more into that in the other presentation. We pin threads, eliminates context switching overhead. improves cache locality, and improves the predictability latency So you can see here in the strategy thread, and obviously it's multi-threaded where it's an infinite loop, or as long as the loop's running, we have a market data queue equaling the pop of the tick. Strategy is quote valid, and so on. So here we're also trying to minimize our latency. With this, we can measure the memory availability, tick to quote, uh, sum in nanoseconds, tick to quote, counter, max latency, nanoseconds again. We have an atomic max updater. We get the current max using this loop. We also have our main. When you see the main, that's usually the end of it. So here we have the command line parsing based upon the arguments listed in the command line. Um, and again, we can initial calculate and launch the back testing. If we're using a file like a CSV, go into live mode, which obviously is not connected in this version. And then we have the model execution. So we're going to do back testing, filing, optimizing. And if we go live eventually, we can add in that functionality for the exchange or broker. Again, in my case, we're using Rhythmic, and I probably recommend going with Rhythmic. Here we have different techniques, okay, with the location and the impact. We have the compiler effects as well. We've kind of gone through that. A couple of things that you might want to highlight. We're just using this G++ self-contained file with everything in it. So we have function inlining. So what we're doing here is there's no in-call instructions for the hot path. We loop unroll, repeat instructions blocks. SIMD instructions like VAP, VAD, PD. These are the different utilities you can run. VMUL, PD for double. And then we can also look at the branch-free coding where possible. We have profiling with perf, code analysis, and the branch misprediction. With the deployer, we've all talked about the building process here, the configuration. We've talked about the shell script that you'd run to run that. We also have the different ways to run the application, expected output we've gone through. And I think we're done. No, not quite. We have the mathematical reference right here for the AS model, mid-price, dynamic, reservation, price optimal, EWA volatility, updated formula, half-life relationship, order flow, raw OFI, enhanced reservation price. And then we have the file structure right here that we've gone through as well. And that's pretty well it. Thanks for watching.